Hi guys, in this video I want to introduce a method to look at some concepts in elementary number theory that hopefully can be useful. The general idea is when we usually talk about numbers, we start with a number axis. And since only the properties of whole numbers are discussed in elementary number theory, we can remove the horizontal line and further make every dot into a box, just to be clear. Wow, and then how will it help? So the first topic I want to discuss is divisibility along with greatest common divisor and least common multiple. Some number of boxes can be combined into units in a longer sequence to illustrate divisibility. So the idea of greatest common divisor is to look for the longest unit that can fill up both sequences represented by the numbers we are given. In a general case, when we are given a and b, a is larger and a equals b times q plus r. How to find the greatest common divisor of a and b? Well, a is like this, and we are looking for the longest d that can fill up both a and b. b composes of some units d's and a as well, so the tail of r in a would have to be a multiple of d here. Thus, d is a common divisor of b and r, but is it largest, or will we say in the graph, longest? Well, we can suppose there is a capitalized D longer than this small d as a common divisor of b and r. Then we can check on a. It can be filled up with capital D's. This contradicts our assumption that small d is the greatest common divisor of a and b. So now we see the GCD of b and r is at the same time the GCD of a and b. Connecting this operation for multiple times is a general idea of Euclid algorithm. Again, we start with a, b, and r. And we simplify our calculation to b and r. Since r is a remainder, it must be smaller than b. So we can put some r's into b and leave a remainder of, let's say, r1. We can keep doing this until we have, let's say, rn minus 1 and rn, in which rn is a factor of rn minus 1. So Rn is the GCD of Rn minus 1 and Rn itself. It would also be the GCD of all the way up, A and B. Well, there is a theorem that can also be illustrated with this kind of graph. When we have LCM AB times GCD AB, we will get A times B. We start with drawing A and B as a sequence of some number of their GCD Ds. Let's say A is alpha times D and beta for B. Notice alpha and beta are co-prime. How about LCM AB? Well, it can be seen as the shortest sequence that can be filled up with only A's or B's. So it is a multiple of D for sure. But how many D's? Well, we can consider D as a unit 1 here. Apart from it, LCM can be filled up with only alpha or only beta, and since they don't have any common factors other than 1, the shortest sequence for alpha and beta, their LCM, is alpha times beta. So LCM AB is alpha times beta times D. And remember, GCD AB equals D. So LCM AB times GCD AB is alpha times beta times d squared, which is the same as a times b. Then the second topic I want to discuss is congruence. We all know that A congruent to B mod M if M divides A minus B. I want to use a method to illustrate some theorems. For example, we have if A congruent to B mod M and C congruent to D mod M, we will have A times C congruent to B times D mod M. So four numbers can all be illustrated with a sequence of some M's and a tail of R1 for A and B, and R2 for C and D. Well, let's first check on A times C. It's the same as some M's times C plus R1 times C. The first part is the same as 0 in mod M, so it can be dropped. And for the second part, we can expand C first and drop the part of M's as well. So we get AC congruent to R1, R2 mod M. See, the exact number of M's doesn't matter at all. If we conduct the same thing to B times D, it's the same as R1 times R2. So AC congruent to BD mod M. Well, some multiplications are involved here. Sometimes we can illustrate it by a larger rectangle with side lengths of the two numbers. For example, we have a theorem saying that if A congruent to B mod M, D is GCD AB and is coprime with M, then we have A over D congruent to B over D mod M. Let's call A alpha times D and beta for B. We have M divides A minus B, thus M divides alpha minus beta times D. It's the same as we say try to use small M times 1 rectangles to fill up a larger rectangle of D times alpha minus beta. There's one thing we have to notice. That is, the way to make it a rectangle is just a transformation to clearly represent horizontally or vertically magnifying the length. So all the smaller blocks can only be put in one direction. Back in this case, vertically, M and D are coprime. So the shortest sequence that can be filled up is M times D. So the length D is not applicable here, since M has to be larger than 1 to make some sense. This leaves us only one choice to put the smaller blocks horizontally, which gives us the hidden information that M divides alpha minus beta, just as the theorem says. Based on that, we have a further conclusion that again, if A congruent to B mod M, and we have D is any common divisor of A, B, and M, then A over D congruent to B over D mod M over D. Let's say A is A1 times D and B1 for B, M1 for M, so that M1D divides A1 minus B1 times D. Just like the last example, we're now using smaller blocks of D times M1 to fill up the rectangle of D times A1 minus B1. Can we put them all horizontally? Well, since D is any common divisor of the three numbers, we have no idea how it would correspond to A1 minus B1 or M1. However, as it's the information we're given, it has to work in every single situation. Again, we're left with only one choice, that the small blocks can only be put vertically, and this indicates that M1 divides A1 minus B1, which is the same as said in the theorem. Thank you very much for watching till here. This video is a response to Summer of Math exposition raised by YouTuber 3B1B. This is so much for the illustration. Leave a comment below if you want to discuss, and see you guys next time.